All right, so now we're just going to state and prove the main theorem about the radius of convergence of a power series. So let's just get right into it. So this is the theorem, 23.1. So we let beta be the lim sup of an to the 1 over n, and r is 1 over beta. Then the series, and of course, so the convention here is if beta is infinity, we set r equals 0. And if beta is 0, we set r equal to infinity. Okay? All right. So then the theorem states that then the series converges for x less than r and diverges for absolute value of x greater than r. And what they don't state explicitly in the book, but which is true, is that if x equals plus or minus r, convergence or divergence is possible. Okay? Okay, so this is the theorem, right? And if you remember, I mean, just from the previous video, this is exactly what I was getting at, right? Which is that whenever an, the sequence of coefficients an, exhibits any kind of exponential behavior, then the radius of convergence is basically the reciprocal of the base of that exponential behavior, right? We need x to be, either growing or well, we need x to be decaying faster than an grows, or if x grows, it can't be growing faster than an decays, right? They kind of compete against each other. And if you look at this, right, remember from the ratio test, the idea here is that beta kind of extracts the base of like exponential behavior of an, at least the largest exponential behavior that you can see in the sequence an, because obviously it might be having multiple different, there might be many subsequences that exhibit different kinds of exponential behavior with different, different rates of growth or decay or whatever. So beta is just the biggest one of those, okay? So the proof of this is actually very simple. It really just uses the ratio tests. Right, we apply the ratio test to the series and x to the n. So they say, right, okay, they call it alpha x. We set alpha x equals the lim sup of an x to the n raised to the 1 over n power, which is the lim sup of absolute value of x times absolute value of an to the 1 over n, which is absolute value of x times the lim sup of the absolute value of an to the 1 over n, which is beta times the absolute value of x, okay? So the ratio test states that if, well, okay, actually, okay, we should be careful about this. They divide this into 3 cases, so, okay. Right. So there are 3 cases. The reason they divide it into 3 cases is just because beta could be 0 or infinity or some non-zero finite number. So yeah, case 1, let's say, right, 0 is less than r. Remember, r is just 1 over beta, so if 0 is less than r, less than plus infinity, then you know, beta is also between 0 and plus infinity. Then alpha x is absolute value of x over r, and the ratio test, sorry, not the ratio test, the root test indicates that the series converges if alpha x is less than 1 and diverges if alpha x is greater than 1. And then this case is equivalent to x being less than r, and this case is equivalent to x, absolute value of x being greater than r, right? So that is the first case. Then case 2 is if r is infinity, then beta is 0. So alpha x equals 0 for all x. So the root test says, oops, sum of a and x to the n converges for all x, right? Because if alpha x is 0, then the sum converges. But if alpha x is 0 for all x, then that means the sum converges for all x, right? And then lastly, case 3, if r is 0, then beta is infinity. So alpha x is infinity for x not equal to 0, right? If x equals 0, alpha x equals 0, because if you go back to the definition, right, if x is 0, it doesn't matter that an might be growing to infinity, right? If x is 0, literally every one of these numbers is just 0 for each value of n, right? So clearly the lim sup will end up being 0 no matter how fast an grows, right? Like even if an is like n factorial raised to the n factorial power, if every term in the sequence is 0, then the lim sup is 0. So alpha x is 0 for x equals 0, but it's actually infinity for all other values of x. So the root test tells us that the series a n x to the n diverges for x not equal to 0. And of course, it converges for x equals 0. Trivially, for x equals 0, it literally just equals a0, right? Okay, so that's the theorem, right? So yeah, I think that will be it for this video. And then in the next 2 videos or so, maybe 2 or 3, we'll look at several examples that kind of show the different possibilities of what can happen. Like when is it an open interval? When is it a closed interval where the series converges, right? What happens if you sort of slide it around on the x-axis and stuff like that. And then we'll kind of conclude with a little discussion of like where we're heading with this, which is pointing towards the idea of uniform convergence for sequences of functions.